Thank you, Dr. Hansraj. Hello, everybody. Today, I would like to give you information, or I'd like to discuss with you a new kind of emergent gravity model, which I believe it will be important for astrophysical, cosmological, and gravitational studies. Let me start with the assessment. Okay. Well, you know, I mean, as we all know, quantum behavior or matter involves wave-particle duality, and this duality holds in flat space-time. Therefore, quantum field theories are inherent to flat space-time. Quantum field theories are defined with an invariant action, and quantum field theories make sense with a UV cutoff, because quantum field theories are not the theories of everything, so they have a certain validity limit, so to say. Let's start with the UV cutoff. Maybe we can ask the basic question we can ask about UV cutoff is that, is it the mass of a particle? If yes, if it is the mass of a particle, then that's a Poincare conserving UV cutoff, because particle masses are, you know, I mean, they are invariance of the Poincare group. Okay, and then we can ask if it is the mass of a vector particle, and if the answer is yes, then we have gauge symmetry broken at the tree level, and this is an explicit breaking. And on the other hand, if the UV cutoff is not the mass of a particle, then it breaks, it's a Poincare breaking UV cutoff, like, for example, the QCD scale or gravitational scale. Scales are not the masses of particles, but they exist as physical fundamental scales, for example. And Poincare breaking UV cutoff generally breaks all gauge symmetries at the loop level, because it's a hard UV cutoff at the end of the day. And my interest, or my fundamental the fundamental question I'll be exploring is this. I mean, essentially, how to restore the gauge symmetries. This question may sound simple, but actually it's a very detailed and a very fundamental question, especially for the red part. For blue part, we know the answer very well, but for the red part, actually we don't know the answer, and it deserves a detailed exploration. But let's start with the blue part, the left-hand side. In the case of a Poincare conserving UV cutoff, what we have is this three-level mass term for a vector field, V mu. And what we do is to kind of generalize or promote this mass term, mass parameter, to a Higgs field and restore gauge symmetries, as it was done long ago. I mean, some 60 years ago, people did it. And it is the basis of standard model, is essentially the spontaneous symmetry breaking. Let's look at now the red part. In the case of a Poincare breaking UV cutoff lambda p, we have this mass term at the loop level, not at the tree level. At the loop level, we have such a mass term coming from the loops. And our intention, our idea, or my approach in this discussion is that I would like to replace this UV cutoff lambda p squared with some Higgs-like field R, which I don't know what it is, and to restore gauge symmetries by this way. I have been thinking about this problem for some time. We've explored different aspects of this problem, and I'd like to share with you my experiences or my findings about it here. The basic question is actually this: what is this Higgs-like field R? What is this field? I mean, how to give a meaning to this field? To see that, before answering this question, before attempting to answer this question, let us discuss first the effective field theory. I mean, if the quantum field theory at hand doesn't have any UV cutoff, we normally use dimensional regularization, calculate our loop integrals as you see above, and it's a very well-known thing. It has gotten a Nobel Prize. I mean, people know it very well. But if the theory has a UV cutoff, if there is a cut on the possible loop momenta, then we don't know how to do this. I'm sorry, we don't know how to construct effective field theory. The reason is that we have to extend this dimensional regularization to cases in which this cutoff is contained, actually, the answer to this question is more or less known. People have already explored this question, and they said that, well, dimensional regularization in dimension 0 and dimension 2, together, respectively, with the quartic and quadratic UV system, which is beautiful. But our purpose is more general than this. We want to include a UV cut of lambda p in addition to the renormalization scale mu. So our purpose is a little bit wider than this. And we have explored this thing recently. Indeed, for lambda p, the UV cutoff to behave as a particle mass, it should not show up in log terms. It should exist only as power law terms. And this constraint is accomplished in detached regularization, so to say. We can detach power law and logarithmic terms. As you see, the red terms here, they take value are non-zero only when dimension goes to 0 and 2, and the black term here remains non-zero only when dimension goes to 4. And then, if we use this regularization, a typical Roob integral takes this form. And as you see, the power law divergences are parameterized by a cutoff lambda p. Logarithmic divergences are parameterized by the renormalization scale mu. And we have analyzed this thing with my collaborators Karahan and Sargon recently. And as you see, what we did is very simple. Instead of taking the renormalization scale mu as the fundamental scale, we included the cutoff scale lambda p as a local scale to the problem. So we have detached two kinds of divergences: power law divergences on one side, logarithmic divergences on the other side. Our effective, our corrections, power law corrections, take this simple form. This is the flat metric eta mu. This term is just nothing but the difference between number of bosons and number of fermions in the theory, proportional to this difference. Second term in the parentheses is this summation. But at one loop, it is just triple trace over the mass square terms in the QFT. The third term is model dependent. In standard model, it is given by top quark-Yukawa coupling of pi squared 3. The last term is again depends on the gauge theory you have in your theory, depending on what gauge groups you have. Standard model, you can compute it very simply. It takes, for gluon, weak bosons, and hypercharge, it takes different values as you see on the right, but these are all calculable. And what we have is that at the end of this calculation, we have total effective action, the level part, logarithmic part, and power law part. I am not interested in logarithmic and three-level parts because they do not create any problem, but I'm interested in the power law part. After working on the power law part, I will unify all parts together to find the total theory. Now let's take our theory to the curved space-time. We were working in flat space-time where quantum field theories make sense. So we want to take this effective field theory to curved space-time. Well, the recipe is very well known, huh? What we do is to use general covariance, under which we replace flat metric with curved metric. We replace partial derivatives with covariant derivatives, where covariant derivatives are with respect to the Civita connection. But differently than the classical field theories, where we are freely changing fields and making redefinitions, we have problems when it comes to effective field theories, because well, to have a curved metric means giving dynamics to metric, but giving dynamics to metric means adding curvature. But the problem is that we cannot add this curvature by hand, because whenever we add a curvature term by hand, we introduce a pair parameter to the effective field theory, which is completely inconsistent because theory is already a loop theory. All loop corrections have been done, and there is no way to add any, pair term. When so in an effective field theory, it looks like there is no place to add this curvature term. When we think about it carefully and systematically, we find that actually curvature term can come only in the gauge boson sector, gauge field sector, vector field sector. The reason is that commutator of the covariant derivatives on the vector fields gives you Riemann tensor, which is the curvature tensor. So we have to deal with this sector only to bring up the curvature term. And I have investigated this in the past. Let me give you one simple way of bringing in curvature into this effective field theory. Let us think about this IV, this kinetic constant involving the coupling CV. CV was the loop factor for gauge boson induced mass term. CV is there as a kinetic term. We can separate this term into bulk and boundary terms by using bypass integration. In bypass integration, these two terms are equal to each other. So in flat spacetime, wave difference is 0. But when you get to curved spacetime, wave difference is not 0, and it involves the Ricci curvature of the Levitt-Vita connection. That means that in flat spacetime, your effective theory doesn't change if you add this difference. It's 0. But in curved spacetime, you obtain a non-zero difference. Indeed, there is no change in flat spacetime, but there is a non-trivial change in curved spacetime, and the change is important because it involves the Ricci curvature. Now, having done with this curvature term of the metric, let's get back to our Higgs-like field. One result is very crucial. It's due to Froggatt and Nielsen. In 2007, they discussed this problem, and they found that in an arbitrary second quantized theory with no presumed symmetries, lack of translational invariance would just be interpreted as the effect of gravitational fields being present, which are not translational invariant. It has the idea is that in a given quantum field, in a given second quantized theory, translation breaking terms are can be identified with curvature. Indeed, in a flat space-time effective theory, the cutoff is the only term that breaks translational invariance, and therefore there should be an affinity between UV cutoff and curvature, something like this. But this affinity should make sense in flat space-time, not in curved space-time. So for it to make sense in flat space-time, we need this curvature to be not the metrical curvature, not the curvature of the Levitt-Vita connection, curvature field of an affine connection, an affine connection field existing in flat space. The correct dictionary is actually an affinity between cutoff and affine curvature. To say all that means is that the Higgs-like field R mu nu can be identified with the rich curvature of an affine connection, where affine connection is totally independent of the metrical curvature. And this is a crucial point, actually. Once we make this identification, what happens is that our power law corrections in flat space-time under this Higgs-like field, under this general covariance, get to this theory, which is what we call is metric Palatini gravity, where there is metric as a curved metric as a fundamental variable. It is curved because we have rich curvature in the last term, and on top of it, it's a Palatini theory because everywhere we have affine curvature contracted with metric. So this is our gravitational theory. This is our metric Palatini gravity or metric affine gravity, whichever you like. I mean, people give these different names to these things, and in general, what is meant is just simple, this simple model or quantity. And we all know that extremization of the action against the affine connection gives the equation of motion for affine connection, which is it tells you that the gradient of this square root of minus determinant of metric times d mu nu tensor should be 0, where d mu nu is this tensor from the action. You can read of it. It involves scalar field, curvature itself, vector fields, and one new constant, the Newton's constant. Newton's constant is induced by loop corrections as supertrace and mass squared over 8 pi. And we immediately see that for this supertrace to reproduce the Newton's constant, which is a huge scale, 10 to 19 GeV squared, it is necessary to introduce new fields into the system because standard model masses cannot satisfy this supertrace. So we have to introduce new particles, we have to have new fields, new particles in the spectrum. But the nice thing is that these new fields, these new particles do not have to interact with us. There is no such requirement in the model. They can just stay as they can just stay as a separate sector which interacts with us only gravitationally, not through the weak, strong, or electromagnetic forces, but only gravitational forces. So, but the Newton's constant inverse, the Planck scale is enormously large. This means that the equation of motion can be simplified in this usual form. It is just simplification as gradient of the d mu tensor being 0. This gives you a solution for the affine connection as the Levy-Civita connection blue part plus a derivative part in terms of the tensor d mu. The point is that under the enormity of this Planck scale, the affine connection can be expanded in powers of Newton's constant in this fashion, and the Ricci curvature can be expanded in powers of Newton's constant in this fashion. These are all derivative terms, and under integration they behave in a specific way, which means that while in the action, that means that when we plug into action, R alpha beta and R alpha beta, the Levy-Civita connection will cancel out to give the blue 0, which means gauge symmetry is got restored. If you plug it in the linear term, we obtain Einstein-Hilbert term, the blue term, with up to double Planck terms. If you plug it in the scalar field part, we obtain scalar field, scalar curvature, non-minimal coupling, as the quadratic, as a result of the quadratic corrections. When we plug in a affine curvature squared term, we obtain the usual curvature squared term, quadratic curvature term, W Planck suppressed terms. And if we sum up all these contributions, we obtain this total term. The three-level part, the loop corrections, the logarithmic corrections, the blue part, the red part, which is the curvature sector. This is our total quantum field theory action in curved space-time. Here, the blue part is quantum field theory sector. It involves the usual interactions which you can test at Large Hadron Collider at CERN, or I don't know, Fermilab in the United States. But the red part is an R plus R squared gravity theory. And in this theory, we have all the stuff concerning the curvature. Let's look at three different properties. First thing is that this gravitational sector, this curvature sector has arisen as a symmetry restoring emergent gravity. That's why a very short, brief name to this thing is Symmergent gravity. This is just a coining name, I mean, to distinguish it from the other emergent gravity models in the literature. The second point is that gravity has emerged from within the flat space-time effective QFT. Gravity is classical, but all its couplings are generated or improved by matter loops. Could you imagine all these couplings, CO, C5, and even Newton's constant itself are loop-induced quantities. They all come from quantum field theory. They are all generated by the underlying QFT. But gravity is classical, and in a sense, what happens is that gravitational interactions are as quantum as the matter interactions. There is a chime, so to say, concord between the gravitation and quantum field theory. I'm not saying that I have solved any a deep problem, but the point is that at the loop level, whole thing is, I mean, this whole action is loop action. But gravity is classical, and there is no problem, there is no tension between this relativistic, general relativity and quantum theory in this sense, in this emergent sense. This is a, so to say, chime between two theories or two approaches, so to say. So let me tell you a little bit about properties and predictions of this emergent gravity. First of all, we have new massive particles in the game. Black hole shadow, photon radius, etc., can provide a good test bed for such a, so to say, emergent gravity model. Higgs mass stability requires dark matter to couple very weakly with us, which is what we see in experiments or searches. Higgs curvature coupling is around 10% in the standard model, and the deviation from this value can reveal the existence of new particles that couple to Higgs field, seem that they don't exist according to Large Hadron Collider experiments. Detection of new particles can wait for high luminosity LHC. Pure Einstein gravity arises. Bosonic and fermionic degrees of freedom in nature are equal to each other, which is something you would expect in global supersymmetric theories. Cosmic inflation is naturally realized in Stravinsky inflation, but you can have other optional, you can realize it with the fundamental scalars as well. New particles do not have to couple to standard model particles. Mismatch stability requires neutrinos to be Dirac, not Majorana. The universe may contain dark stars, dark planets, even dark galaxies, because this extra particle sector forms a dark sector, and it can happen. In fact, the recent Gaia observation about this thing, this dark star, seems to be interesting in this sense. I have investigated these things partly, only partly, with some collaborators of mine. They did excellent job in realizing these tests, and I am indebted to them a lot, especially Professor Örgün. He led all these discussions, all these studies, essentially. I'm thankful to him. This is our gravitational sector in Symmergent gravity. There is this Einstein-Hilbert term, linear part, there is quadratic curvature part, and there is vacuum energy part. Vacuum energy is contains two parts, three-level and loop correction. Loop correction is very simple. Super trace mass to power of 4 over 64 pi squared. If you want, you can simplify this expression a little bit. If you assume that bosons and fermions have a common mass, it takes such a simple form. And from this simple form, you can make a generalization like this as a one-parameter parameterization. But you don't have to do that. I mean, if you know the spectrum, you can compute it explicitly. But if you don't know the spectrum, which we don't know actually, it is very hard to deal with this total energy. And such a simplification is very useful indeed. We made these simplifications with Professor Örgün and other collaborators, Becky Pantic, Rahim Baev, and others. In this theory, Einstein field equations take this form. You can have two kinds of solutions. One solution refers to the de Sitter solution or anti-de Sitter solution, depending on the sign of your vacuum energy, which we have just discussed in the previous page. The second class of solution, a new stuff, is actually asymptotically flat variable scalar curvature solution. And in this case, you can, in each case, in all cases, you can probe the parameter CO in the equation, which is characteristic feature of the Symmergent gravity. And also, you can probe the vacuum energy under mild assumptions. Okay. This new solution of asymptotically flat solution is due to Buchdahl, actually. Nguyen recently reinvented this solution. I and my collaborators, Professor Örgün, Patrick, and Pulice, we are investigating this this space-time solution. And also the de Sitter and anti-de Sitter solutions were realized by others in the literature already. One kind of solution is therefore Schwarzschild DS, Schwarzschild ADS solution. Let me just remind you that CO is number of bosons and minus number of fermions. It is a model parameter, and the corresponding change in the Schwarzschild solution is this blue thing. And this blue function involves this DS or ADS part involving R squared, the distance squared, radial distance squared. Another solution is asymptotically flat solution, Buchdahl-Nguyen solution, as I was mentioning you. Solution, there are AR, BR, and CR constants. And these constants have been found as solutions by Nguyen recently. Phi, conformal factor phi, obeys such an equation. And the equation involves the usual constant CO of Symmergent gravity. And it is related to number of bosons minus number of fermions in the theory. And thank you very much for your attention.
Thank you so much, Prof. Demir. That was a fantastic and insightful talk, and a thorough explanation and setup of Symmergent gravity. Perhaps for the students that are on here, maybe it's the first time they're hearing about this kind of gravity as you explained. The floor is now open for questions for Prof. Demir. You can raise your hand or type into the chat box and I can ask it to him. So I have a question.
Sure.
It's quite interesting, as you mentioned, that the gravity has emerged from within the flat space-time effective quantum field theory. I think it's on the slide where you explain the logs and powers before introducing the curvature. You were saying that the last term can be modified. Sorry, yeah, it's like way at the beginning.
Let me go to there. I don't just remember.
I think it's before curvature, before when you're talking about the flat one more, I think.
Okay.
One more. And I think it's the one, yeah, this. So this term here, this gets changed according to, like you said, if it was a gluon, or it depends on that, right?
Yeah, here I assume that electroweak symmetry is not broken. All gauge bosons are massless, gauge symmetries are exact, and we put a UV cutoff lambda p to the theory, let's say standard model. Then we compute loop corrections. It turns out that the gauge bosons or vector fields in our theory all get masses, and these masses involve lambda p squared as the scale, and in front they have this loop factor CV. For each gauge group, there are these loop factors.
Yes. Okay. Yeah. All right. Thank you. Any further questions for Prof. Demir? Yes, Prof. Hansraj.
Thank you very much, Prof. Demir, for your excellent talk.
Thank you.
Very fascinating topic. I have never thought about this topic along these lines. I was always, when we deal with gravity theory, we wonder what to do with higher derivative terms.
Yes, that's right.
I'm wondering how it impacts on the models. The last slide that you showed, I didn't quite get it, but is there a conformal geometry with the standard GR models? Or?
Yeah, let me come there. First of all, dealing with gravity is quite non-trivial when we start with quantum field theory, because quantum field theory makes sense in flat space-time, and gravity means curved space-time. In curved space-time, we don't have Fourier transform, therefore we don't have wave-particle duality. Therefore, it is really there is really a very big tension. My idea was to follow the spontaneous symmetry breaking idea, the standard model, original, let's say, construction, and apply it to a Poincare breaking UV cutoff, so that since it's Poincare breaking and since curvature is automatically Poincare breaking, obtaining a correspondence between UV cutoff and curvature to obtain this kind of Higgs-like mechanism to induce gravity. This was my approach. And the nice thing is that there are of the order of M-Planck squared suppressed and higher order terms, of course. They involve derivatives of the scalar fields and vector fields in this red part. These terms are higher derivative, of course, but they are suppressed, very much suppressed by Newton's constant, so to say. They never play any discernible role in this regime, so to say. But if you look at the first three terms, it is so beautiful that we don't have any higher curvature term, so to say, because R squared is the last power, highest power. And CO is 0 for when bosons and fermions are equal in number in the fundamental QFT. That means that we are able to predict exact Einstein gravity when nature is kind of fermion boson symmetric, so to say, in terms of quantum particles. I don't know, was it a question or answer? I'm sorry.
That was very good. Yeah, no, I appreciate that. Just that the last slide,
Sure.
if you can, that where you spoke about the static spherically symmetric metric.
Yeah. I'm sorry. Maybe I was in the wrong slide. I'm sorry. You mean this metric, huh? This one.
Yes.
This is a new solution, actually, Hansraj.
So these are not. So this is not a conformal factor, the phi there.
Actually, it is like conformal factor, actually. Conformal factor, you can say conformal factor, but this thing obeys this equation on the left. This was derived by Nguyen. I'm citing him here, as you see. But what the interesting or restrictive thing is that this solution is valid only up to linear in phi. Linear in phi.
Linear in phi, okay.
Yeah,
Good.
the phi squared and higher order terms have not been discussed or checked or analyzed by the author.
Thank you.